Okay, everybody, there's been another slight wrinkle. I'm informed that Jesus Gonzalez is currently on an airplane somewhere which does not have a Zoom connection. And so it is on. And so Shmuel Weinberger is in fact going to substitute, and I assume that we will have Jesus's lecture this afternoon, but in any case, Shmuel is going to talk to us on Morse theory, Morse complexity.
Okay, thanks. You know, I feel awful that I'm so happy to be here. You know, I mean, it's like very, very, you know, I mean, the last time I was at Fields, it was during COVID, and it was electronic, and it was awful. I mean, it was as good as we could do at the time, but being here in person is, you know, personally, it's great, it's wonderful, and I'm seeing a lot of old friends. But the fact that the occasion is that we all miss Fred is makes this all bittersweet. And then, of course, you know, there's the therapy issue that you then feel guilty for feeling good and all that. But, you know, but anyway. Do I need to repeat that, Tony? Tony feels awful that I'm here. Okay. Okay, I hope everyone got that.
Thank you.
Yeah. No, anyway, so Fred was really a wonderful guy. You know, I mean, you know, he was a nerd before being a nerd was cool. You know, he'd go up to you and like, he would talk to you like, you know, in this stream for like, I don't know how long it would go on. And, you know, and then by the time you'd get to ask the question, it was that, what was the very first thing that you said? But it was really wonderful. He had just such enthusiasm, and he was curious about so many things. I think that this meeting is, you know, I mean, it's not only a tribute to the mathematics that he did, it's also a tribute to the mathematics that he was interested in. So I'm going to start off, so I'm going to talk to you about some joint work I did with Fedya Manin, who is here, and Bena Chichiku, who is at Brown. I believe he's going to be here. I don't know if he's here yet. Oh, he is. Okay. Okay. I saw someone raise their hands. Actually, my vision has decayed during this past year, so I don't actually see beyond the second row at the moment. But anyway. Okay. Hi, Bena. Anyway, and this was motivated by some questions that Gromov asked, and in fact, Gromov sort of answered some of them too, and I couldn't understand what he was talking about. And then, like after a year, I sent him an email, and then I didn't understand the email he wrote to me back either. So it might be that what I'm going to talk about, Gromov knew, or you know, but I'm sure he didn't do it this way, because what we're going to do is kind of has very inelegant aspects. Okay, so anyway, so here's the question. Okay. Okay, so let's say the Morse complexity of a manifold is just the minimum number of critical points for a Morse function on M. Okay. Okay. So, you know, what can I say? Okay, so this is sort of a basic. So by the way, everything, everything that I'm going to be saying has, lots and lots of analogs and variations, as is typical with a Gromovian question. And for almost everything, the answer will be, I don't know. Okay. So anyway, so this is sort of a thing that we've studied for a very, very long time. For example, for any homotopy sphere, right, this quantity is 2. Okay. So, and, a lot of us learned about Moore theory, in fact, for the proof of that theorem. Okay. So now what Gromov wanted to know about, and there's sort of a lot of things you can do to estimate this, right? We have Morse inequality. So if I have a specific manifold, right, I mean, I would, I could look at the homology and get an estimate for it from, out of that. In high dimensions, in Smale's approach to the Poincare conjecture, he showed that there are sort of converses to the Morse inequalities. Okay, so that if you know the homology of a simply connected manifold, you could figure out and you could mimic the simplest chain complex that would explain the homology. Okay, and okay, so that's cool as far as it goes. When you're non-simply connected, it becomes a much more complicated thing. And then there are even very, very non-trivial chain complex questions, right? I mean, how, you feel that, oh, if I just knew, maybe I could mimic everything I see in the algebra, but then it turns out that you can't understand the algebra. Okay, I mean, so this is, of course, part of the great irony. One tries to do a lot of things by algebra, say, over the group ring of the fundamental group, there are things where, allegedly one has a complete analysis of the problem because you've reduced it to algebra. But then in most of the cases, maybe what you should really think is, oh, I've only reformulated the problem in terms of algebra because I can't do the algebra, right? The thinking about the manifold as being, say a hyperbolic manifold, there it's a beautiful thing. But if you think about it as being the integral group ring of the fundamental group of a hyperbolic manifold, maybe you're not just in love with that object. It doesn't speak to you the same way. Okay, so Gromov asked about the following thing. Suppose I take alpha being a homology class in a space X. Okay, this seems to be like a pretty general kind of thing. Okay, and the question is, when is the Morse complexity of alpha positive? Okay, so now obviously this doesn't make any sense yet, but I mean, he didn't ask it in this bald way, but what I just want to do is, but this is going to be the question that I want to address. Okay, so let me now unpeel this a little bit. Okay, so for sort of step 1 is, assume that there exists a G that maps some manifold to X such that G star of the fundamental class of M is alpha. Okay, and then, this will be evidence that the Morse complexity of alpha is less than or equal to, by definition, the Morse complexity of M. Okay, if I have a representative for it, then that representative has whatever Morse complexity it is. Okay, and so that's sort of the beginning of the story. Okay, so if I have a representative, this is the one that I'm going to use. Okay. Now, of course, if I might find a more efficient representative of that homology class, right? Maybe, if we would like doing surfaces, I might find one with smaller genus, and then I will lower the Morse complexity, right? Right. So we're going to be infamizing over the M's. Okay, so of course, step 2 is that M doesn't exist, but thanks to Renee Thom, there exists a G from M to X such that G star of the fundamental class of M is K times alpha. Okay, where K is some integer. Okay, so now I could at least define the Morse complexity of alpha is the inf over m and g of 1 over k, the Morse complexity of m. Okay, I apologize for my Blackboard technique. Okay, does everyone understand the idea of this question, right? So you have an x, okay, okay, and so right, and by the way, right, so this fits into the conference, right? It's homotopy theory. Okay, if x is homotopy equivalent to y, then clearly the Morse complexity of alpha and the push forward of alpha. Yes, so this fits in. Okay. So anyway, so this was Gromov's question, and the thing that Gromov said that set me off is, you know, he mentioned this question, and then he commented, he asked about for which manifolds M is the Morse complexity of the fundamental class of M not 0, and he gave some examples. And if I get to them, I will give all the examples that Gromov gave. Okay, I mean, so it will exactly coincide with the question when you restrict to the fundamental class of manifolds. Okay, but I want to put things in this larger, you know, just discuss this a little bit from a larger perspective. So, by the way, so I'm not going to ask a show of hands, but some of this might like ring familiar to people. If instead of asking about manifolds and handles, okay, if you were to think about manifolds and pseudo manifolds and triangulations, right? So you could always represent a homology class by an oriented pseudo manifold, okay, and then you could count the number of simplices, but you still go through the step 1 and step 2, okay, right? So then this is, you know, this is the notion of simplicial norm. Okay, and you know that's a very deep and valuable theory. And for example, the simplicial norm of a hyperbolic manifold is the volume of that hyperbolic manifold. Okay, so even though, you know, you go ahead, you give this definition, and it's homotopical in some sense, right? But it really captures a great deal of geometry, and it's non-trivial in every dimension. Okay, I guess. I don't know what a hyperbolic 1 manifold is, and it doesn't apply to the circle. Okay, let's not worry about that, but it's non-trivial in all dimensions above 1. Okay? Okay, so, you know, so you could be led to this question also if you wanted to do a handle version of simplicial norm. Okay, so the first theorem that I should say about this, I'm not sure, I'm not going to prove anything, okay? Okay, I mean, maybe there's one trivial statement because you're supposed to prove something in every talk, but okay, but I'm going to try to explain things. So at the moment, I'm just going to sort of, you know, tell you the phenomena and what we know and what we understand and what we don't know, okay? So the first theorem about this is that the map from x to k pi 1 of x1 is norm I was going to say it's norm preserving. Maybe that's a little stronger than what we prove. Okay, let me just say that. Now I'm being careful because I'm talking to humans. The kernel of the map from hi of x to the homology of the group consists of elements of norm 0. Okay? Okay, so now it really fits into the conference, right? Because it's supposed to be about algebraic topology and groups. Okay, and now, okay, your whole space, you know, goes away, and all that's relevant is the fundamental group of the space. Yeah, the kernel of this map, right? So you just go from X to K pi 1 of X1. Anything in here can, oh, norms, Morse complexity of Morse complexity equal to 0, right? So for all of these guys can be represented, with arbitrarily small number of handles, right? If you multiply by a big number, it goes down. Okay. Okay. The next thing is that. So by the way, so again, this is exactly what happens in the simplicial norm story. So it's sort of like maybe a little bit of a familiar story. So theorem B is that it's identically 0 in odd dimensions. Okay. So dimension 1 is obvious, right? You have the circle, and then you could take the k-fold cover of the circle and kills it. Misha's observation for why this was true in dimension 3 is because 3 manifolds, unless they're pathetic, pathological, or something, always have finite covers that are bundles over the circle, right? Egel's theorem. And then once you have that, then you can take a bigger cover, and it's still going to be a fiber bundle over the circle, and it's still going to have the same fiber, right? So the Morse complexity is at most 2 times the number, 2 times the genus, or well, 2 times some function, linear function of the genus that I'm not going to figure out at the moment, right? Of the fiber, right? I mean, so okay, so in dimension 3, you could see this for, through a deep theorem of Egel, and let's see. So I'm going to. So I'd like to state a conjecture. Okay. And later on, we'll, at some point, I'll figure out who this conjecture is due to. I mean, I'm willing to take credit, but but I think that other people believe things and have said things that would imply this, and etc. So, what? Oh yeah, to be honest, okay, this is a digression, okay, but yeah, no, I mean, but this was a topic of some interest at a conference I was just at in Cambridge, where there was a lot of discussion. But anyway, there are different theories of conjectures. Okay, so there are people who make conjectures, and then when their conjecture is disproved, oh, they're really mad at the person who disproved it, and and like they think it's really, really awful. And no names mentioned. Okay. I'm not going to repeat that, Tony. But then there are people who are, so like I've made a lot of conjectures. I'm kind of profligate. And sometimes I conjecture what I believe, and sometimes I conjecture the opposite of what I believe, sort of laying down the gauntlet to the community. You can't even disprove this idiotic proposal. Okay. And now, of course, when you do the second one and they prove it, then you seem like a prophet. Okay. So there's sort of, so anyway, so I tend to be, I'm not worried so much about whether the conjectures are true or not. For me, the focus is whether they, do they stimulate ideas, and, are they useful? Now, the other kind of conjecture, I don't want to knock those people as being narrow-minded. I mean, they're really great. I mean, like there are things like the Riemann hypothesis. It's a great conjecture. And then you go ahead and you build assuming it. And the theory is that if you keep building on things and deciding, and then coming up with a really great conjecture that would improve that conjecture, you keep building mountains upon mountains upon mountains. And then maybe you get, that gives you a view in which you could solve everything that you wouldn't have gotten to if you didn't have, these things to hope for. So, it's just a very, very different style. Okay. Anyway, so that's the end of the digression about conjectures. But anyway, so these are, so by this I just mean a locally symmetric manifold. Okay, so you should imagine that G is semi-simple. Okay, so with non-positive curvature. Okay. And so let me say it like this. The Morse complexity of the fundamental class of this manifold. Oh, why don't I just put the bracket like that? Equals 0 if and only if the Euler characteristic of this is not 0. Okay? And what I will explain is this direction, which Gromov had. I heard it online. He mentioned it in some conferences, and I think that what we have in mind isn't unrelated to is, is a variation of what Gromov thought about. Okay, so let me just point. Where does this come from? So one way to get information about Morse complexity is just the following. I look at my map. So if let's start off with this one. If the Euler characteristic is non-zero, then suppose that, if I have a manifold, right, representing a cycle, how would I represent 2 times the cycle? Okay, so there are at least 2 dumb tricks, right? One is to take 2 copies of the manifold, and that doesn't help you, okay? Because that increases it, and then you divide and it decreased, nothing changed. Okay. The next thing you could do that's a little more intelligent is you could take a 2-fold cover of the manifold if the manifold had a 2-fold cover. Okay. Now that sometimes works, right? Like, if you do that with a torus, you take a cover of the torus, then you're going to be making things smaller. Okay. So now this is a good business. I could take a manifold, and if the fundamental group is residually finite, I could take bigger and bigger or deeper and deeper covers and then renormalize the Betty numbers, okay, by that process. And then there's a wonderful theorem called the Luke approximation theorem that says that that limit actually exists. So we know what this process buys you, okay, and that limit is, has an analytic interpretation. It's the L2 cohomology. Okay, and so this process is something that sort of really, it's really interesting. We don't know, say, for example, if you use mod p Betty numbers instead of mod 0 Betty number, instead of characteristic 0, whether the limit is independent of the chains. We don't have an interpretation of what this looks like. It's sort of, one of these great subjects. Another subject that sort of relates to Morse complexity, if I would be asking about the number of critical points of index 1, rather than asking the number of critical points, then I'd be asking how many generators does the group have? And I believe that Wolfgang Look has speculated that the first L2 Betty number is exactly what the limit of the is what's called the rank gradient. You look at how many things it takes to generate the group, from the point of view of what you get by looking at L2 cohomology. Okay, so now you could reinterpret old results in harmonic analysis as the statement that, okay, if you look at G mod K, its L2 cohomology is non-zero exactly when it's non-zero in the middle dimension. Okay, and so in particular, when it's odd dimensional, there is no middle dimension. Okay, okay, and that this is exactly equivalent. Well, if it's non-zero in the middle, okay, well, so then you're having some kind of Betty number in the middle, and this turns out to be exactly equivalent to saying that the Euler characteristic of the original manifold was non-zero. Okay, so the hypothesis that you're 0 suggests, if you believe an analog with respect to higher simplices and for higher cells in the CW decomposition, okay, one could believe, and I believe there are people other than me who believe this, that in fact when you take these kind of towers of covers of these manifolds, okay, then you could find CW structures with them that are sublinear in complexity, where just by the complexity doesn't at all see the attaching maps, right? But it just counts the number of cells. And this is maybe not unreasonable. And there are various groups, I think like SLNZ, where this phenomenon is observed on some skeleton of it. So this might be bolder than anyone was willing to go with in public, but I have no shame. Okay, so that sort of, part of this is very suggested by certain trends in geometric group theory. And the other direction is the one that actually is a theorem, though. Okay, so now what about the other direction? If the Euler characteristic is non-zero, okay, so let me just firstly point out, if the Euler characteristic is non-zero, then the stupid idea that I suggested doesn't decrease Morse complexity. Okay, right? I'm going to be looking at my G mod K mod gamma. It had non-zero Euler characteristic. When I take a 5-fold cover, the Euler characteristic gets multiplied by 5. So when I divide, right? So the Euler characteristic is, of course, right, a lower bound on these kind of complexities. Okay, and that's exactly right. So I just wouldn't be able to achieve this just by looking at covers. Okay. Right? But the point of this is that, of course, if I represent 5 times the class alpha, there's no one will go ahead and tell me that I should therefore factor through a 5-fold cover of the space X. Okay? So therefore, so just the first thing you try doesn't give rise to this, but it's potentially the case, right? And that's what the content of this theorem is. Okay? All right. Are there any questions about this so far? Okay. Okay. So let's put this in a slightly larger or maybe more algebraic topology context. Okay, and this. Instead of homology, we can consider, okay, Bordism. I never know what's a good symbol to use for Bordism. What? Omega? That's still permissible? You should know, I mean, I have a hang up that I keep feeling that I'm supposed to say that instead, but I don't like saying that. Okay, so instead of looking at homology, we could look at Bordism. I'll put the SO on top just for a split second, okay? Okay, that instead of asking the question about homology classes, okay, I could ask the question about Bordism classes, okay? Same definitions, etc. Okay, and now, okay, so from the point of view, so I'm just going to do this to seem learned a little bit. Okay, so there's a map from Bordism to KO homology, which assigns to a manifold its signature operator. Okay, if this is gobbledygook, don't worry about it. It'll go away after a little while. I mean, okay, and then of course I could go ahead and I could push it into the K pi 1. Okay, and this map here is studied by people obsessively for many decades, and these are called the higher signatures of the manifold. I have a manifold with a map to X. Whether I care about it in X or not, I don't care. But if I think about some fundamental group around, okay, this is, I guess, the Poincare dual or something. It's a refinement of the Poincare dual of what were called the Novikov higher signatures. Okay, so this is kind of like this is sort of a basic object. So let me point out, so if we were thinking about fundamental classes for higher dimensional homology of simply connected things, I'm saying that everything goes away. Okay, but if I were doing boardism, maybe now it's a different question. I take a boardism class and I want to know, can I, I could want to try to ask, what's the simplest Morse complexity of a representative of that boardism class? Right, so this is this is something that, you could have asked without multiplying and dividing, and then you could do very, very refined things. But if you're a crude person, you multiply and divide. Okay, so are there any boardism classes other than what you saw in a point, that are there? And the answer is yes. The signature, right? I'm not going to, if I take the connected sum of a lot of copies of CP2, CP2 has Morse complexity 3. If I take the connected sum of a lot of copies, I get K plus 2 or something if I have K copies. So when I divide it, it goes down to 1, and that's the signature of CP2. Okay, so does anyone who I can see want me to review the definition of a signature? Okay, I don't see anyone asking for it, but maybe that's not fair. Let me just remind you, if I have a manifold whose dimension is a multiple of 4K, I look at its middle cohomology, I diagonalize the quadratic form, and there's the positive part minus the negative part, that quantity. So firstly, it's obviously homological, so it obviously bounds, things like handle structures, okay? And it's amazingly a boardism invariant, okay? So so when I asked a boardism question, then the signature of the manifold arises as being an obstacle. Okay, and theorem A, the variant of theorem A is that if you're asking the thing about boardism, all that's relevant is the higher signature. Okay, whatever that is. That's some kind of non-simply connected guy that takes into account that all the signatures of submanifolds where the submanifolds can be blamed on the fundamental group. Okay. Okay, so now, okay. So here's the idea for theorem 1, for theorem A, okay, which is there exists a subject called surgery theory. That says that higher signatures are the only possible restrictions on boardism classes of simple homotopy equivalent manifolds. Okay, so the classic example is there was a theorem, I think, of Peter Kahn in his thesis, that if you look at product of CP2s and you look at the manifolds homotopy equivalent to that product, you can get all the Pontryagin numbers that you could imagine, except for one, and that restriction is the one given by the Hertzebruch signature formula that says that some combination of those has to have signature equal to 1. Okay, so that's a simply connected version. And then there's sort of a fancier version which puts it all on wheels. Okay, that says when you have a fundamental group, it's not just a signature, it's the higher signature is the only thing that could possibly obstruct modification of simple homotopy equivalent manifolds. So then a key proposition somewhere in there is to say that simple homotopy equivalent manifolds have the same Morse complexity. Okay, and this is of the same level of depth as the Poincare conjecture and surgery theory, et cetera. So you have to finesse something in dimension 4. Let's not worry about that. But in higher, but this is sort of the source of the phenomenon. Okay, right? Simple homotopy equivalent manifolds. They're very, very different in terms of geometry, but you could somehow mimic the handle body structures that make one into the other. Of course, an enormous amount is hidden in not understanding the glue, right? The mapping classes by which you connect the handles to each other. That's where all the geometric difference between the manifolds is. But, at some level of abstraction, these are the same. So now once I know that simple homotopy equivalent things are having the same Morse complexity and then different ones. Okay, so that immediately gives you theorem A prime. Okay, at least at philosophy. Okay, details. Okay, and let me just comment about from A prime to A is that if you look at the Bordism. Okay, I'm going to write this is true better than rationally. But if I just take Bordism and I tensor over the Bordism of a point with the manifolds with signature equal to 0. Okay? I mean, I think that's what I want to say. Let me not say it like that because that's too fancy. Okay, I want to say, so this will be signature 0 manifolds, okay? And then, if I just take the ideal generated by these, the graded ideal generated by these, okay, I mean, that's what it is in English. This is the homology of X, okay? So the key point then is that I want to show that, so this is clearly how the different problems are related to each other, right? I mean, I'm sort of getting rid of guys where some signature is 0. And now what does that mean in our CP2 example, right? CP2, I just said we can't in Bordism get rid of them, right? But on the other hand, CP2 connected some with CP2 bar, okay, that maps by degree 1 onto CP2, okay? And I leave it as an exercise why CP2 connected some with CP2 bar, where you find manifolds of bigger and bigger degree over it without increasing Morse complexity. So you do that and with other things on complex projective spaces, and you could sort of mod out by this. And okay, so so it's sort of just a little trick away. Okay. Okay, so let me just think. Why is it 0 in odd dimensions? Okay. Yeah, okay, so theorem B is way easier. Or let me just say different. I mean, because, because it's based on a different black box. I mean, I threw surgery at you as a black box. Okay, now I'm going to throw a different black box onto you. There's a theorem of Terry Lawson. And it was given another proof subsequently by Frank Quinn. And it's that all odd dimensional manifolds, all closed, that went without writing, have open book decompositions. Okay, so let me remind people what an open book decomposition is. Okay, so here's a picture, right? So I have this I have my manifold. What should I call it? Z, because I'm here. Okay, so I got Z, and Z is supposed to be an open book. So it has B, which is a binding. Okay, so B is a Z minus 2-dimensional submanifold. Okay, so the classic, by the way, the classic example is I have the 3-sphere. Inside of it, I have the unknot. The unknot is going to be the binding. And then the pages, the unknot bounds a disk, but it bounds more than one disk, right? You could fiber the complement of the unknot by a whole circles family of disks. Okay, so there's supposed to be pages P sub theta for theta lying in the circle. Okay, so that's an open book decomposition. They have been incredibly valuable in foliation theory and in contact geometry and so on. And it's a wonderful fact that in odd dimensions, there's no obstruction to constructing these. Okay, so with the classical theorem of Alexander in dimension 3, and in higher dimensions, it's the theorem of Lawson and Quinn. And now we could do the stupid idea again. Okay, because if I have one of these things, I can take a branched cover where I branch along the binding. Okay, just do this thing and have theta go through several times, and that will be something which has a degree k. And now the number of handles that all of those manifolds have, you could bound in terms of what the complexity of the binding, the complexity of the page, multiply that by 2 because it's an interval direction, etc. Okay, so this explains the whole odd dimensional case. Okay. Okay, so here is now speculation. G mod K mod gamma has an open book decomposition. If and only if the Euler characteristic of G mod K mod gamma is not 0. Okay. Oh, okay. My watch has very gently given me the 10-minute warning. Okay, so I should be wrapping up. Okay. What? It's an Apple Watch and it's connected to my phone, and my phone, put an alarm. No, it's not like it asks me. It does ask me questions sometimes, but anyway, yeah, but that's not okay. So let me just point out that a corollary of the theorem is that when this Euler characteristic is not 0, then there's no open book decomposition. Okay, so in particular, even dimensional hyperbolic manifolds don't have open book decompositions. So this is one of these ironic things that I mentioned before. The paper of Quinn gives necessary and sufficient conditions on a manifold to have an open book decomposition. The simply connected version of this was Winkelkemper theorem, which is that a simply connected manifold of dimension bigger than 4 has an open book decomposition exactly when its signature is equal to 0. Okay, and so Quinn defined some algebraic thing, but it turns out that it's kind of an algebraic thing that we don't understand at all. And that's part of I think the interest in this subject is that there are the pieces of algebra that in the past were viewed as solutions to problems, where if you actually care about the answers to the problems, you discover that they don't at all help. Okay, so maybe what I'll just do is explain in one very simple case, which is trivial by other means, about how you go ahead and prove this theorem. So absolutely everything I'm going to tell you about, the theorem part of this, it all generalizes, and all of the hard work is generalizing what I'm about to say. I'm going to show you the really easy thing. Okay, and what I want to do is I just want to explain why the Morse complexity of if I take a surface of genus bigger than 1, why this one is positive. Okay, so I want to give you a sophisticated proof of this. Okay, and this should really be, of an M4K plus 2. Okay, so let me just make it concrete. Okay, so if you do K theory, that makes various things 4 periodic, etc. Okay, so if you like, I take this surface and cross it with a manifold V of dimension 4K, where the signature of V is not 0. Okay, so now it already becomes a less trivial statement. The fact that up to Bordism, I can't lower the handle complexity of this. Okay, right? So that's the one. Okay, and if you believe this, then you should believe that after you do a ton of representation theory and you use fancier index theorems, blah, 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 then you end up getting the results. Okay, so now the proof of this is can be viewed completely geometrically. There is a bundle over the surface of high genus that is called the Atiyah-Kodaira bundle. Okay, I don't remember what the genus of the fiber is. This is the generator of H2 of the mapping class group, okay, which is an object that Fred liked. So I can't call this manifold. I'll call it W. So this is called the Atiyah-Kodaira bundle, okay, for obvious reasons, because they both discovered it around the same time. Okay, and the key interesting thing about this bundle is that the signature of W is not 0. Okay, you know, I mean, suppose that I would have squared W. So then I would be having an 8 manifold, and then I'd have a base, which is a 4 manifold, and a fiber, which is a 4 manifold. And these 4 manifolds, all the 4 manifolds, right, this square and that square have signature 0, but the total space has non-zero signature. Okay, so this kind of business that you can have, you know, this is kind, you know, for bundles that have no monodromy in homology, signature is multiplicative. But when you have monodromy, then signature is no longer multiplicative. And this manifold W is the instantiation of it. Okay? And now the key point is that if I have to say this. So if I have F mapping a manifold W 4K plus 2 to a surface, say of genus 2, I could then consider the pullback of Atiyah-Kodaira. Right, I could just pull back this bundle, okay, and then I will have, okay, it's clear I can't handle the complexity of my notation, okay. This will be a manifold of dimension, I guess, 4K plus 4, and it has a signature, and the signature is proportional to, you know, the image of that push forward of the fundamental, you know, of the, you know, the higher signature in H2 of the surface. Okay, this thing that we were talking about, basically the fundamental class, is what measures this, right? If I have another map from a surface of degree D and I pull back the Atiyah-Kodaira bundle, the signature of the total space gets multiplied by D. Okay, and that argument really wasn't a surface argument. It applies to all manifolds. It's really a Bordism argument. Okay, and so that's sort of the proof for surfaces, and it would be a proof for products of surfaces and things like that. And in general, what you reflect on is that you don't really need the surface manifold. Okay, when you analyze what the signature of the total space is, it really could be interpreted as being the cohomology of the base with coefficients in a local system associated to the fiber, where the local system is the monodromy of this element in H2 of the mapping class group. Okay, so that's the thing that you have to generalize. Okay, and you know, and that's what we do. I mean, we follow in the footsteps of George Lustig's thesis, where he did things like this for the symplectic group. But it turns out that whenever G mod K mod gamma has non-zero Euler characteristic, and you know, there are enough representations of the Lie group G into groups of Hermitian forms of the relevant kind, so that you can do it. And unfortunately, we need taxonomy and calculation, et cetera. It's completely ugly, which is very disappointing given how simple the statement is. But anyway, but I have hopes. My hope is that our methods are entirely superfluous to the phenomena, and that, you know, we'll get a deeper understanding, you know, as we think about this and some of its implications. Like for open books, there are implications in knot theory and Smith theory. And I mean, there are a whole bunch of places where we've gotten by pretending that by reducing things to algebra, we've solved the problem. But in this is the case, the only way we have any information about the algebra is via analysis and Lie theory. So that can't be right, but I'm done.
Are there any questions?